So I hope you can still see my screen. Hello.
Yes.
Yeah, good. So let's wind up with the numerical integration. So as usual, we'll define and then give different methods of carrying out numerical integration and do an example to see how or what we're supposed to do. So here I will derive, I will not derive the methods. I'll list them without deriving, but I'll encourage you to check the derivation in the textbook and the previous class lecture that I shared with the class. So numerical integration is the process of evaluating a definite integral from a set of tabulated values of the integrand. The process of evaluating a definite integral from a set of tabulated values of the integrand. So we'll have an integral, say I, from a to b of f of x dx. So if you recall from your calculus, this function is what you call the integrand when we write. So this f of x is what we are calling the integrand. And so this process of integration is key when the function f of x or the integrand is not easy to evaluate using the methods we discussed in calculus 2, or when the function is not given, but just the values of the function at specified values of x are given in a given interval, is when the process of numerical integration becomes useful. So this process when applied to a function of a single variable is known as quadrature. So the way we treat the problem of numerical integration is the same way we treat the problem of numerical differentiation. That it is from the interpolating formulas that we obtain the formulas to carry out the integration process. So like that of numerical integration and numerical differentiation. is solved by representing the integrand f of x by an interpolating polynomial then integrating it within the given limits. So I will state different methods of carrying out numerical integration without deriving, but I'll encourage you to check the derivation process. They are not very hard to follow. So the first one is what we call the trapezoidal rule. So trapezoidal rule is not very new. You did it in Form 4, but we'll still discuss about the same. So to evaluate integral from a to b of a function f of x with respect to x, we'll have h over 2 into y naught plus yn plus twice y1 plus y2 plus y3 all the way plus yn minus 1. So these y are called, so y naught, y1, y2, all the way up to yn are called ordinates. Then h is given by b minus a over n. Where n is a number of subintervals, or sometimes we call them strips. So this is what we have. So just to describe what you are saying here is if I have this as our function y equals to f of x, then I have this point x equals to a, this point x equals to b, so the integration from a to b of the function f of x dx, we interpret this one as area under the curve y equals to f of x, and these lines x equals to a and x equals to b. So this area trapezoidal rule states that we divide it into n trapezia. Then this first value x at x naught is the same as, we call it x naught. Then this point we call it x1. This is x2, x3, x4, x5, etc. Up this is xn. So given that y is f of x, then the value of the function at x naught will be f of x naught. So which we can write it as y naught, or we can write it as f naught. So the value of this height, the height or the size of this line here will be y naught. The value of y, the value of the function on the y-axis will be y naught units. Similarly, the value of the height of this line will be f of x1 or f1 or y1. So when we add the area of this trapezium plus the area of this other trapezium plus the area of this other trapezium plus area of this other trapezium, all of them, when we join them together, then they'll give a rough estimate of the area between this curve and this line, x equals to A and x equals to B. So each of these trapezia is called a strip. And so this is the definition. You get a sum of the end ordinates, then plus twice the sum of the middle ordinates, then you multiply by h over 2. H is actually the size of each strip, or the width of each strip, simply given by difference between the limits divided by how many strips or subintervals you have. Then another numerical integration method is what we call the Simpson's 1/3 rule. And then the Simpson's 1/3 rule is also just sometimes called the Simpson's rule. So this works. This is used when the number of strips or subintervals is even. So when you don't have an even number of subintervals, then this method will not work. That should be very clear from the start. So number of strips or subintervals is even. So that the formula is integral from A to B of f of x dx will be given by h over 3 into y naught plus yn plus 4 into y1 plus y3 up to plus yn minus 1 plus twice into y2 plus y4 all the way up to yn minus 2. So it's always good to know when to apply a formula. That's why we are specific on before we give the formula when conditions which makes it to be justifiable to be applied. So for you to use Simpson's 1/3 rule, you must ensure that you divide your region you divide the interval A to B into an even number of steps or subintervals. So that is when you'll be able to apply Simpson's one-third rule. If the number of steps is odd, then this method will not apply. So you say this structure can as well be written as h/3 into sum of end ordinates plus 4 times odd sum of odd ordinates plus 2 times sum of even ordinates. So that's why, in short, someone can write the Simpson's one-third rule as h/3 into E sum of end ordinates plus 4O plus 2E. So where O means odd ordinates, E means even ordinates. But the key thing before you apply that formula, you ensure that your region is divided into an even number of subintervals. Then 3 is what we call Simpson's 3/8 rule. Simpson's 3/8 rule. So the condition for this, even before we start, is that the number of intervals should be multiples of 3. This is applied only when the interval A to B is divided into whose subintervals which are multiples of 3. You should take note of that. So this formula will be integral from A to B of f of x dx will be 3h/8 into y0 plus yn, sum of the end ordinates, then plus 3 into y1 plus y2 plus y4 plus y5 plus yn minus 1 plus twice y3 plus y6 plus y9 all the way plus yn minus 3 Then please also check there's what we call number 4. there's what we call Bool's rule. Take from the textbook the formula. And then there's also what we call Weddell's rule. And then there's what we call Romberg's integration. So please check the structure of those rules. So then now let's give an example to illustrate how we can deal with this. First 3 rules. For example, evaluate (0 to 6) dx over 1 plus x squared, then using trapezoidal rule, B, Simpson's third rule, C, Simpson's 3/8 rule, D, or maybe let me call it, so this is D, find, let me call it Roman 1, then Roman 2, find the error in each of the methods in one above. So in the first case, I want us to take n to be 6. This also n to be 6. This also n to be 6. So what happens now? The first thing is to identify your f of x. So if you relate this to the general integral from a to b, f of x dx, then what will your a value? If you have to compare the general integral and the integral we have at hand, what is the value of a?
0.
0. B?
6.
6. Then n, we have been given to be 6. So n is 6. So can you find the value of h?
Yes.
Actually,
1.
1, because it's simply b minus a over n. We'll have 6 minus 0 over 6, which is 1. Now, what is our f of x in this example? Compare this general and this integral we have at hand.
1 over 1
1
plus x
over
squared.
1
x
over
squared.
1 plus x squared, correct. So you make a table value. So f of x is 1 over 1 plus x squared. So x, and then f of x. So 0. So the spacing we have calculated to be 1. So 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. 5 plus 1 is 6. And that is the endpoint. So to get f of x when x is 0, you simply have f of 0 is 1 over 0, 1 plus 0 squared, which will give us
1.
Hello?
1. So 1 over 1 plus 1 squared is 1. So this will be 1. Then f of 1 will have 1 over 1 plus 1 squared, which will be
0.5.
0.5 or a half. And I encourage you to, when you are dealing with such kind of problems, unless it is not possible to write your answers in exact form, and exact form are fractions, then put them in fractions. Because sometimes decimals will create or introduce a round of errors, which we are trying to run away from. So leave your answers in fraction. Then when x is 2, f will be 1 over
5.
1 over 5. 3 will be 1 over
10.
Over 10.
10. Correct. Then 4, 1 over
17.
17. 5,
1 over 26.
1 over 26. And lastly, 6,
1 over that 7.
1 over 37, correct. So I encourage you, when you are solving problem in this course, we must have been told by our teacher that the main objective of doing this course is to reduce errors in computation as much as we can. So when you use decimals, it will actually truncate some digits. For example, when you're writing 1 over 37, if you convert it into decimal form, there's a high chance that you will leave out some digits. So you are highly encouraged to write your numbers in exact form as fractions, the way you have here. So then by default, this first number is what we call y naught. So this is y naught. Some people can call it f naught. Then this is y1, or you can call it f1. This will be y2 or f2, y3, y4, y5, y6. So A, trapezoidal rule. So trapezoidal rule will be integral from 0 to 6 of dx over 1 plus x squared is the same as h over 2 into y naught. Now our yn is 6, y6, then plus twice y1 plus y2 plus y3 plus y4 plus y5. Then we substitute appropriately. So this will be a half, because h is already 1, into 1 plus 1 over 37, plus twice into a half, plus 1 over 5, plus 1 over 10, plus 1 over 17, plus 1 over 26. Can you kindly use your calculator to get the answer to this? What will be the final answer here? Okay, the sum of those fractions, multiply by 2, then add the answer to the sum of the two endpoints, multiply by half.
1.41
1.41,
1
1,
1.411, yeah.
1 is fixed.
No.
That's where the problem starts. Is that answer exact as 1.411?
No.
So write you need to write all the digits the way they are.
1.410
07
7,
98
9,
851
5
5 to 1.
81
After this 9, 8 followed by
581.
581. Okay. Yeah, so you write all the digits. There is no rounding off unless you are told to do so when you're solving all the numerical methods problems. Because our main objective of doing this is to reduce errors in computations. When you round off, then you're introducing round of errors, which we don't want. Then B, Simpson's third rule. So Simpson's third rule will have, by definition, integral from 0 to 6, 1 over 1 plus x squared dx will be h over 3 into n coordinates will be y0 plus y6, then plus 4 into pointer Simpson's third rule. 4 is multiplied by the sum of which ordinates?
y1
y1
plus y3
plus y3
plus y5
plus y5, because we're multiplying 4 by the sum of the odd numbered ordinates, and then plus 2 into
Y2
y2 alone
plus Y4
plus y4 plus
y6.
up to
yeah,
Y4.
I've catched you.
No,
I've
no.
catched you. So
To
remember,
Yeah.
when we say the sum of the end ordinates plus 4 times the sum of odd ordinates plus 2 times the sum of even number ordinates. Please, once we have used an ordinate, if it happened that one of the end ordinates is an even ordinate, and it has already been used in the first bracket, then of the starting term here, you don't repeat it. So no ordinate should be used more than once in these formulas. So because next was to be y6, but y6 was the last ordinate which has already been used here, then you stop here at y4. You don't add y6 here. Those y6 is even ordinate, but because it's already an endpoint, then it has already been taken care of. So we don't write it here again. So therefore, our h is 1 over 3 into y0 is 1 plus 1 over 37 plus 4 into y1 is a half, followed by y3
1 over 10
1 over 10 plus
1 over 26
1 over
26
26. Then plus twice into y2 It's a
1 over
fifth
5
plus
1 over 17.
1 over 17.
1 over 5
Correct.
plus 1 over 17.
Yeah, correct. So then can you evaluate that and tell me the answer?
1.366
1.366
17
17
3413.
3413. Okay. I know the last three digits can vary from one person to another because of the accuracy of your calculator, but that will be taken care of. But whenever you're solving this kind of problems, please do not do premature rounding off. Then lastly, Simpson's 3/8 rule. So the integral from 0 to 6, 1 over 1 plus x squared dx equals to 3h over 8 into y0 plus y6, then plus 3 into so this was the, let me remind you, this is how we were, these were the formula for the Simpson's 3/8 rule. So remember, in our case, we are reaching y6. So what will be the reduction of this formula? After writing y0 plus y6, I'll have 3 into
Y1
y1
Plus y2
plus y2
plus
plus
Y4
y4
plus y4
plus
plus
y5
Y5
plus y5. Then plus 2 into
Y3
y3
plus Y no.
no y3 like that.
just y3, because remember, these two multiplies the sum of oddness, which are multiples of 3. But because we have already used y6, then you don't write it here again, okay?
Yes.
An ordinate in this, all these formulas can be used only once, can't be used more than once. So we'll have 3y1 plus y2 plus y4 plus y5, then plus 2 times y3. So this will be 3 times 1 over 8 into 1 plus 1 over 7 plus 2 into a half plus a fifth then y4, y5, y4, 1 over 17, 1 over 26. Then plus twice y3, and y3 is 1 over 10. So can you also simplify and tell me the value of this?
That 2 should be 3.
That should be 3. This will be 3. Yeah. Can see people are following. Good. So can you simplify? And work out.
$1.35
1.35
70
70
80
80
836.
836. So that's what we have. So we have done A, B, and C. So part from and 2 was to find the error in each of the computations we have done in A, B, and C. So recall error is simply exact value minus approximate value. I remember in all these methods we are discussing under numerical integration and differentiation, there are approximation methods, they are not exact. So the answers we are getting use those formulas are not exact answers. They're just approximate or close to the actual values of the either integral or the derivative, depending on the problem you're solving. So remember to get exact value is the integral from 0 to 6 of 1 over 1 plus x squared dx. So what is the value of the integral 1 over 1 plus x squared using your calculus concepts? When you integrate 1 over 1 plus x squared, you get? These are standard integral, whose values? From your SMA 104 work, what is integral of 1 over 1 plus x squared dx?
Is it tan inverse or?
Tan inverse of x, correct. Tan inverse of x. So if it's indefinite, you add a constant c. So here, we just have tan inverse of x from x equals to 0, x equals to 6, which is the same as tan inverse of 6 minus tan inverse of 0. Can you tell me the numerical value of this? Use your calculator to find tan inverse of 6 minus tan inverse of 0.
One point four.
What then?
1.4.
1.4.
056.
056.
47649.
47649. Is everyone having this same answer? Or there's someone with a different answer? Anyone with a different answer from this? Anyone with a different answer from this? I expect another answer apart from this. Any person with a different answer? Tan inverse of 6 minus tan inverse of 0. Use your calculators and tell me, what are you getting? Any other answer?
I just have the similar.
Same. Any person with a different answer? There's a reason as to why I want a different option. This may not be the correct answer.
80.
80 point
80.53767779.
80.537677.
7779.
79. Are there people getting this?
Yes.
Yeah,
Yes.
good. Yeah. An answer but a wrong answer, but good for learning. So I expect it is possible for you to get this. So for people who are getting this 80.53, there are many people who might be getting this answer. It's an answer but a wrong answer. Good for learning. So that you don't repeat this mistake next time. So the reason as to why we are getting, some people are likely to get this answer 80.53 is because of the configuration they are using in their calculator.
Yeah,
So for people
their
who are getting
calculator is
80.3, the mode is in degrees. Okay?
yeah, they are in degrees.
Yeah. So if you are dealing with trigonometric functions, an expression involving trigonometric functions, plus logarithmic functions, plus exponential functions, and with their respective inverse functions, or even hyperbolic functions, and you want to get a numerical value of that expression, please note that if your mode is in degrees, all your answers will be wrong answers. So the correct mode should be radians. Yeah. So for those who are getting 80.53 is a genuine mistake that is likely to be committed, but don't commit it next time. It is because your calculating in the wrong mode. So whenever you want to get any numerical value involving trigonometric functions, hyperbolic, log, exponential, and their respective inverses, ensure that you change the mode of your radians to mode of your calculator to radians to get the correct answer. So this is the correct answer. So if you are using your calculator, ensure that the mode is in radians to do the commutations. So this is what you'll have. So therefore now I need not to waste time to calculate errors. So you can easily now calculate the errors. You'll be picking this number, this exact answer we have, and then you subtract from each of the answers we have gotten in part A, B, and C. And remember, by default, when we say error, we imply absolute error. So when you get that this number, the exact value, minus what we have as approximate value, if you get a negative sign, ignore that negative sign and just take the magnitude of that value. So the error by default will imply absolute. So therefore now, with that error, you can as well calculate the relative error, just taking the error over the actual value of the two value. And once you have the relative error, you can compute the percentage error, and then you'll be at home. The method which will give you a smaller error in magnitude will be the better method to apply. So I leave it as an assignment for you to do the error computations. You can go further and compute the percentage errors and make a verdict. Which of the three methods is better than the other in terms of the approximation of the given integral. And the better method will be the one that will give a smaller error magnitude. So with those many remarks, I wish to stop there. I'll give an assignment on what we have covered today, and we'll have a cut next week, same time. So have a good day. And then I remember I shared some previous class lectures. I've been teaching this course from 2020. So the previous classes, the lectures were recorded and put on the same place. So you can use it to make reference for revision and any other as far as this course is concerned. So if there's no question, I can stop there. And if you need more reference materials, feel free to ask. I'll share them if you need more other references. These notes I can share after this, and also the class recordings for those who are having network issues. Sawa. Sawa, have a good day. Okay.
Same.
Bye.
You too.
Good day.